Hi, Braylon. It's just you so far. Let me give everyone else a couple more minutes to see who else joins. I see Julio just joined, Jonathan, Dwight. Nice to see you all. Zachary, Megan. All right. So people are going to be chiming in just to make sure we're all on the same page. So let me share my screen with you. Screen. All right. So I have uploaded stuff onto Canvas, and it might look different than it looks on your page because I'm using a tablet right now. But I have your notes for today listed, how to get to today's Zoom meeting, and I also have uploaded changed your schedule a bit. I have omitted some sections so we're not rushed, and I also provided where you can turn in your homework. You can also turn your homework under assignments, so you can find it there as well. I just have those two right now. I will upload everything onto Canvas that you turned on so far so that everything is uploaded. Are there any questions before we begin? So everyone can hear me and see my screen?
Yeah. Yes.
Yeah.
Yes.
Okay, good. So please ask as many questions as you would like. Oh wait, hold on. Amazon's coming. Huh. All right. So let's continue with this next section, 4.3, exponential functions and applications. Before we begin, let me remind you some rules for exponents. So this is when we have a negative exponent. Sorry for my dog. All right. So there's a rule for when we have a negative exponent. If we have, for example, some number and it's raised to a negative exponent, then we can go ahead and to deal with that negative exponent, we simply go ahead and to deal with this, we keep our exponent, but to get rid of the negative, we write it as 1 over, and we now have our exponent of 1. So let's do a number example. Say I want to do something like 1/2 raised to the negative 2 exponent. To deal with that exponent of a negative, I would have to write it as 1 over 1/2. So when it's a fraction, it essentially flips it. So now it becomes 2 over 1, which is just 2. So it'll be 2 squared. Maybe I started with one that was a bit too ambitious. Let me try one more. What if I had 2 to the negative 2 exponent? Okay, so then I would go ahead and simply take the negative and write it as 1 over. So it'd be 1 over 2. So we have 1 over 2. And that exponent of 2, we keep it. So then we can evaluate. So 1 over 2 times 2, 2 squared, we get 4. Hopefully now that last example we did, that first one made a bit more sense. So you might have to deal with negative exponents. Remember, if it's a number, you just write it as 1 over your number. And that gets rid of the negative exponent. And if it's a fraction, you just flip it. and that will deal with the negative exponent. Because you're doing 1 over a fraction like we did here, 1 over a fraction, and that essentially just flips your fraction. So I just want a quick review on an exponent rule, an exponent to a negative power. Okay, let's continue with 4.3 exponential functions and applications. So we have 4 objectives. The first one says to draw the graph of an exponential function, to understand the exponential function with a base e, perform calculations involving exponential expressions, and applications involving exponential functions. Okay, so as we continue to work with this section, it's all about exponents and how we go about graphing exponents. Just with anything that we've graphed in the past, we can always do a chart to help us and guide us through what we're working with. We can always do a chart if we're ever unsure of what we're trying to graph. Okay, so let's take a look and read this section. As the name implies, exponential functions involve exponents. However, unlike quadratic functions, which have a variable with an exponent of 2, a polynomial equation, I lost myself, or a polynomial function, which is often have variables with exponents of 3 or 4 or higher, or even rational functions, which can be expressed as negative exponents. Exponential functions differ from all functions in functions we have studied in this course so far, then the variable is now the exponent. So this is a definition. A function of the form f of x equal to b to the x, where b is greater than 0 but not 1. Let's go over these 2 rules. So why can it not be 1? Well, if our base was 1, then 1 to any power, well, that wouldn't be anything. 1 to the first power is 1, 1 squared is 1. You would just get never-ending amounts of 1s. So it wouldn't give us anything exciting. It wouldn't produce an exponential function. For 2, we have that b must be greater than 0 or positive to avoid non-real complex values. All right. So let's continue with an example. That first example. Let's start a discussion with the graph of the exponential function with the simplest exponential function, f of x is equal to 2 to the x. All right. So give me 1 second.
Hi.
Hi everyone. I'm trying to move things around. Let me mute myself. Unmute. This is gonna work. Okay. I was trying to add myself in the laptop as well. That didn't work. I'm sorry. All right, so let's continue forward. So we have this function. Now we can let x be whatever we want it to be. And just like before, we can pick any points that we'd like. So let's start with some negative values and 0. So here we have a list of negative values. And here we have some positive numbers. So this is just going to be our number in the exponent. So if I choose x to be 0, we have 2 to the 0 power. A number raised to 0 power is always 1. Now my exponent is going to be negative 1. 2 to the negative 1 gives us a 1/2. Now we're going to choose our exponent to be negative 2. We have 1 over 2 squared, which gives us 1/4, and so on. Now let's work with our positive numbers. So we have 2 to the 0 power, which is 1. Now my exponent will be 1, so I have 2 to the first power is 2. We're going to let x be our exponent, which is 2. 2 squared is 4. And so what we have created is we have points, right? So we have points like 0, 1, negative 1, and 1/2. -2 and 1/4, -3 and 1/8. You already have that one there. It's just repeated. 1 and 2, 2, and we got a 4, plugged in a 3, and we got an 8. So now we can go ahead and plot our points. And here are all the points we graphed. Now, if we wish to, we can go ahead and plot our function. And our graph will look like this. Now, if we continue to pick negative values, more bigger negative values, we will never get 0, right? Because we're always going to get 1 over some number. So it's just always going to be a very, very small number. It continues forever to that small number, so we say it continues to negative infinity. Now, if we continue to pick bigger values like 4, 5, 6, it's just going to be going up, 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 and up. So we would say that it keeps getting bigger, and we would say that it continues on to positive infinity. So here, let's go ahead and write down, well, it explains what we did. On the left side, we see that x is approaching negative infinity, just like we did right here. The points we found for f of x equals 2 to the x power are getting closer and closer to 0 without ever reaching 0. As in our discussion of rational functions, we call the line y equals 0 the x-axis, or the horizontal asymptote. So this part right here, highlighted, this part right here is referring to this line because we're never going to cross it. We're never going to get a negative number, right? We're never going to get a negative number. We're just going to get bigger, a fraction that gets smaller and smaller and smaller towards the negative side. So we have essentially an asymptote there. Let's continue with the right side. Unlike rational functions, the horizontal asymptote only controls one end of the graph. We see that as x approaches infinity, for the x equals infinity, the points we found for f of x equals 2 to the x power are increasing and taking off from the horizontal asymptote. So we see that those numbers are getting bigger. This part right here corresponds to this. They're getting bigger, right? So are there any questions so far? If at any moment you have a thought or a question, feel free to chime in. Otherwise, you'll forget your question and then we'll never get it asked. Moving forward, so we're going to do another example. There are traits that every exponential graph will possess. One end will flatten out towards a horizontal asymptote, while the other end will take away from the horizontal asymptote while never changing direction. For these reasons, drawing the graph of even the more complicated exponential functions can be accomplished with a simple two-step process. Find the horizontal asymptote and plot 2 points. So let's go ahead and do that. So we have these 4 functions to consider: f of x, g of x, p of x, and r of x. Before we consider those functions and to locate the asymptote, let's go ahead and start here. It reads, we will revisit our chapter 1 discussion regarding the graph of g of x equals a times x minus h squared plus k as transformations of a parabola, f of x equals x squared. Do you remember how that works? Recall how this h, if it's a plus h, we move to the left h. If it's a minus, we move to the right. Do you remember how that k works? If it's a plus k, which way do we move? We move up, right? And if it's a minus k, we move down. Well, it works the same way. So let's continue reading. So it reminds us that for function f of x, x would shift the graph left or right. A would stretch or compress your graph, so it make it wider or skinnier. And k would shift the graph up or down, just like we left it above. So the way we read that for an exponential function is the same way. But remember how we had parentheses? Think of your parentheses as your exponent. Your exponent will take the place as parentheses did for a parabola. So let's continue right here. Starting with f of x equals b to the x power. That has the horizontal asymptote at y equals 0. So the parent graph has the horizontal asymptote at 0. And we're considering these possible shifts. H would shift the horizontal graph to the left or right. So this H that's right here. And K would shift the graph. A would stretch or compress and possibly reflect the x-axis across the x-axis again, leaving the horizontal asymptote at the right. And highlighted reads, the only value in g of x equals a times b raised to x minus h power plus k that would change the horizontal asymptote would be k. So that's very important. Shifting the horizontal asymptote up or down. Okay, so we only have to look for that k. So if we're adding or subtracting a number, that's going to shift our horizontal asymptote up or down. And that's all we really want to look for when we're looking for horizontal asymptotes. So take a look at A. Do we have anything being added or subtracted on the side of our function? No, right? So we can say that there's no shift up or down. We have that same horizontal asymptote at x equals 0 at our x-axis. Let's take a look at the next one. So do we see how we have that +4 being added right next to it? Well, that's going to cause our whole graph to move up and down. Well, in this case, move up 4. So therefore, our horizontal axis, this should have been a y. It's a horizontal line. Our horizontal asymptote is going to move up 4. So we now have y equals 4 as our horizontal asymptote. And for C, do you see how we have a -1 on the side? That's not in the exponent's place. So therefore, we're going to shift our horizontal asymptote down 1. So my horizontal asymptote is y is equal to -1. Last one, D. We have pi raised to the x minus 4 power. Again, notice that there's no plus on the side that is not on the exponent's place or a minus. So there's also no shift. So we still have that x-axis for our horizontal asymptote. So it's y equals 0. So this is how to find your asymptotes, how to find your horizontal asymptote. That's a breakdown with some examples and some explanations. Any questions so far? All right, let's move forward. Now that we know the location of each horizontal asymptote, we can graph the curve by finding 2 points and determine which side to determine which side goes toward the asymptote and which side goes away from the asymptote. So our exponential functions are always going to look the same way, just like parabolas. Parabolas were U-shaped, either open up or open down. Exponential functions, like our first example, they go like this, or they might go like that. They can also be reflected over the x-axis, so they can go like this or like this. But generally, the first two is what you'll see. So that's why it's saying that you only need to know 2 points, because as long as you have your asymptote, you just need to know which way it's spreading up or going upwards. All right, let's continue. Because the domain of every exponential function is -infinity to infinity, that means that all x values work, right? There's no limit to what x can be. You can plug in a negative x, a positive x, and there's still something going on for your function. So our domain is negative infinity to infinity. Any x value can be used. But as you will notice in the following graphs, choosing x values that keep your exponential portion of each exponential function small is wise. So you want to pick numbers that will fit into a graph, because you don't want to draw a graph that has 100 tick marks or thousands of tick marks. You want to stick to like maybe 15 or 10, right? So let's do this next example too. Graph each of the following exponential functions. So the first one, A, is f of x is equal to 5x squared. So let's plug in 2 points. So here it's saying let x be 0. So you plug in 0, you get 1. So you have a point 0, comma 1. Now you're going to let x be 1. So you have 1, comma 5. If this notation throws you off, you can always do a chart, right? So your function is 5 to the x power. You're plugging in a 0. You're plugging in a 1. 5. X will now be 0. A number raised to 0 power is always 1. So I get a 1 for my y. 5 raised to the first power. Well, 5 to the first exponent. That gives us 5. So I have my point 0, comma 1 and 0, comma 5. Just like we do right here, right? And it's just a preference thing. If you want to do a chart, feel free to do so. Okay, now let's do one more, just so you can see what your author was trying to warn you of. So what if you do 2? Let's do one more here. 2. 5 squared. Well, 5 times 5 is 25. So that means I have the point 2 and 25. Isn't that a point that might be just a bit too big to plot? That 25 is kind of scary. I do not want to do 25 tick marks on a graph. So that's what he meant by use your points wisely, so that you don't have to do too many tick marks for your graph. All right, now here we have a graph of our points. We see we have our asymptote at y is equal to 0. And with our 2 points, we can locate what our graph is going to look like. So we have this exponential function. They look like L's, mirrored L's. Okay, let's do this next example B. Before I move forward, are there any questions? Okay, you can always email me your questions. All right, B, your question is g of x is equal to negative 3 times 2 raised to the x minus 1 plus 4. Whoa, that's a lot to do. And for some reason, I'm sorry about that. For some reason, I don't like reading the math sideways, but I can go ahead and do it side by side, or going down, working my way down. So let's do this first one. This first one is saying let x equals 1. So let's go ahead and do that. So we have our function, it's negative 3 times 2. Our exponent will be 1 for x minus 1 plus 4. Okay, let's go ahead and work this out. Now, even though it doesn't have parentheses, we want to make sure we want to simplify what's with our exponents first. Okay, and this is the same work you have on that line right there. So we have negative 3 times 2, 1 minus 1 is 0. All right, so I have 2 to the 0 power. Let's figure that out first. 2 to the 0 power is 1. All right, follow order operations, right? So I have negative 3 times 1 is negative 3 plus 4, you get 1. And that's our answer right here, right? Let's do let x equal 2, which is the one we have right here. All right, so this means that for our x right here, we're going to plug in a 2. Let's do that work together. So I have negative 3 times 2. My x will now be 2 minus 1 plus 4. All right, let's do that part in parentheses, our exponents first. So negative 3 times negative 2. 2 minus 1 is 1 plus 4. All right, I have to follow order operations, so we have to work with that exponent first. So I have negative 3 times negative 2 raised, oh, that's not negative 2. I know I wrote negative 2. We have 2 raised to the first power, which is just 2, plus 4. All right, follow order operation. So we have to multiply before we add. So I first have to multiply these two. -3 plus times 2 is -6. Plus 4, we get -2. And that's our answer right here. So I just have that same work that's on your paper. I just wrote it down and explain each step. All right, so I have my points. I have my point 0, 1. I'm sorry, 1, 1, and 2, -2, right? This is x and this is my y, so 2, -2. So I have plot my points, and I see that my horizontal asymptote is at -4. I'm sorry, +4. So we have it right here at 4. I have y is equal to 4 as my horizontal asymptote, and my graph is below it. So I go ahead and connect my points, making some type of L shape. And if you're ever unsure, you can pick more points. So another wise point to choose would have been 0, right? So you can always do x is equal to 0 and input into your function. So you have -3 times 2 times 0 minus 1 plus 4 and get an answer there. You should get a fraction. All right, moving over to C. So we have p of x is equal to 1/3 raised to the x plus 2 power minus 1. Okay, let's do these parts together. Let's do this work that your paper shows. Let's do it together. So we're gonna let x equal -2. Okay, we let x be -2. I have 1/3 raised to my x will be -2. -2 plus 2 minus 1. All right, let's simplify what's in our exponents. So I have to do that first. So I have 1/3, -2 plus 2 is 0, minus 1. All right, what is a number raised to the 0 power? It's 1. So I have 1 minus 1, we get 0. So my first point that we found is -2 and 0. Okay, let's try -1, the one that we have right here, -1. X is equal to -1, so this means we're going to substitute in a -1 for x. So I have 1/3 times -1 plus 2 minus 1. All right, let's simplify my exponent first. So I have 1/3. -2 plus 1 is just 1 minus 1. So 1/3 to the first power is just 1/3 minus 1. We want to find a common denominator, right? So I have 1/3 minus 3/3. We get -2/3. So my second point that I found is -1 and -2/3, the fraction. Let's plot my points. So before plotting my points, I have to list my horizontal asymptote, right? So my horizontal asymptote is y is equal to -1. So I have it right here, y is equal to -1, and I plot my 2 points. And it seems the one that's higher up tells us which way our exponential function is opening, right? And exponential functions will always have like this L-like shape. It can be upside down or it can be backwards, but this L-like figure. Now I'm gonna run by D, but I won't do it so in detail. So pi, it's a button in your calculator, is about 3.145 something blah blah, right? It's a rational number that never ends. So here it's plugging in values for x, and we get these 2 points, 1 and 3.4. So I have these exponential functions here, and we see that we have our asymptote at y is equal to 0. So wherever your highest number is, it's where it's going to keep going on to infinity. Your lowest number is going to get closer to your asymptote whenever crossed. All right, so just like pi, so we know pi is an irrational number and it's a button in your calculator. There's another irrational number that works exactly like pi. This number is e. And you have it right here. E is about 2.7. So if you want to be a nerd, whenever your friends celebrate Pi Day on March 14th, you can be an extra nerd and celebrate E Day or Euler Day, which is February 7th, 2.7. All right, so let's go ahead and read this introduction. In this section, we have discussed exponential functions with bases of 2, 5, and 1/3, and even pi. All numbers that satisfy requirements, that b must be greater than 0 and not 1. For our next topic, we will introduce the irrational number e as the base of our exponential function, often referred to as a natural exponential function. Just as pi is an irrational constant that can be approximated as 3.14, e is a non-terminating, non-repeating decimal which can be approximated 2.7. So that's e. And not that you, so where this number comes from is when one studies calculus, the number e is derived from the expression of the limit of n approaching 0 for 1 plus 1 over n raised to the n. So we don't really need this, but in case you were curious as to how that happened, that's where it comes from. Pi comes from the proportion to a circle and a diameter. So whatever this number is, the measurement around with proportion to the diameter, that's what pi comes from. It's a special proportion for circles. All right, so let's go ahead and do example 3. Graph each of the following exponential functions. So for this, you will have to use your calculator. If you don't have a calculator handy, you can always use your cell phone. You have the e function. If you tilt your phone sideways and you get more options in your calculator, that's where you can find e. So e to the 0 power is always 1. A number raised to 0 power is always 1, with the exception of 0. And e to the first power, well, it's itself 2.7. So this is how our exponential function for e looks. We have it right here. So it behaves just like any other exponential function. It looks like a backwards L, and we have an asymptote that we locate, and it has the same shifts just like the examples we did before. So let's take a look at example B. G of x is equal to -2 times e to the x minus 3 plus 5. So before even beginning, I can always locate my asymptote, right? I have a horizontal asymptote at y is equal to 5. Now I need to graph my function. Because I have that negative, I know that instead of looking like this, it's going to be like folded over by our x-axis, right? So it's going to be reflected this way. So it should look like this. But we'll see that. So we're gonna plot 2 points, and we're gonna use our horizontal asymptote to guide us for the lower part of our function. All right, so we plot 3 points. So we're gonna let x equals -3, which we have here. Let me walk you through this work together. So we have -2, e raised to the -3 plus 3 plus 5. Now, why do they start off with -3? Well, because in your exponents, when you add them, it'll make 0. So that's a good point to start, where you make your exponent 0. So I have -2 times e to the 0 plus 5. All right, what's any number raised to the 0 power? It's 1. So I have -2 times 1 plus 5. If this is -2 plus 5, you get 3. So our first point is -3 and 3. And here we have -2. When you plug in -2, you get a decimal. -4.436. So here we have our points. The one that's closest to your asymptote continues on it for -infinity, and the other one continues on to +infinity. Now notice I glanced over this one because you need your calculator for this one. Okay, and it leads us into our next part. How do we go about using a calculator? So it depends on which calculator you're working with. If you're unsure, we can always talk about this after I go over the lecture. You can show me your calculator and I can tell you maybe what buttons to push. So for the most part, I see calculators have something like a e to the x button. And it might not be a button. Maybe you might have a button and in yellow letters or colored letters, green letters or something, or purple, it'll have e to the x above the button. If that's the case, you need to use the shift command to access the other buttons for each main button. So let's read this. When working with E in example 3, we use the approximation of 2.718. For our continued use, E, and for evaluating most exponential functions, you will be using calculators. When studying exponential function and using a calculator, 2 buttons become useful. So this is in general for when you're working with exponents. We're used to working with maybe a square button, maybe an x square, but we're going to be working with exponents that are not always square, something like to a third power, fourth power. So you might have a button that looks like this, right? Or maybe a caret. So play around with the calculator. So if I want 3 to the third power, I might have to press 3, then the button, and then the 3 again to get 27. Because 3 to the third power, this means 3 times 3 times 3. And while you can go ahead and punch them separately, you can always take use of your button as well so that you don't have to do too many calculations. Now here has a way you can verify. To verify a button on your calculator, calculator's exponential button in question, and to practice how to use this button, calculate the following rounded to decimal places. So I'll give these a try in your own time. Practice 3 raised to the 2.4 power. Your answer should be 21.67, or the next one, 2.4 raised to the 1.9 power, you should get about 5.28. So those are some you can try. Moving on, this first button works well for finding the value of an exponential expression for any numbers you wish to type into a calculator. Earlier, we discussed the number e, which can be approximated as 2.7. This is not a number I would ever wish to type in or even memorize. This is where your second calculator button is useful. So as I was saying, you can take a look for a button that looks like this. And if it's not a direct button, maybe, like I said, it's like right above your button, there's sometimes different colors. Maybe you can find it that way. And if so, you should have a second button or a shift button, and that helps you access that matching color. And if you don't have a calculator today, that's okay. We can always address your calculator questions on Wednesday when we meet again. But let me know. So these are some you can try as well. Try these out just to make sure you're punching things correctly. Because some calculators, you have to punch things in weird orders. So it's just a matter of testing it out. All right, exponential applications. I think this is our last tidbit of our section. So working with exponents, there's these exponential functions that we work a lot with calculating interest. So let's go ahead and continue reading. When calculated and added to a savings account or charged because of a carried balance on a credit card, interest is the most common example of an application involving exponential functions. So consider $4,000 at 6% annual interest invested for 3 years, but with interest calculated and paid monthly for the 36 months. So what that means is every month out of the 3 years, it's gonna calculate that 6% in, right? So that first month, you get $20. Okay, you're gonna take those 20, your new balance, and multiply that by your new balance and your month, right? So we have $20. So we add that into our balance. So we're adding these up. So if we want to find out what we're getting after 3 years, we will have to do this 36 times because after each month, we would have to add the amount to our initial balance. That's a lot of work. So that's why I didn't spend so much time talking about it. So there's a different way you can do it, and it's right here. In general, the formula for calculating the account balance of $3 at an annual interest rate of R compounded by n times of a year for t years is this beautiful formula. A is equal to P times 1 plus R over N times N times T. So just to help you remember better, we have everything laid out, right? We have P is our dollars, R is our rate, N is times per year, and T is years. So let's list that. P is your initial account balance for your principal. Your starting balance, also called your principal, that's why it's the P. We have a R for your percent. R is your rate, which is your percent. But whenever you work with percent, always change it to decimal form. In decimal form. And lastly, we also have N, which is times per year. So to think about this a bit more, if we see a word like monthly, it means 12. If we see semi-annually, it means twice a year, right? It'd be a 2. If we see something like quarterly, it would be 4 times a year, right? So there's some words you might see. You can also see daily. In that case, it'd be how many days in a year. And lastly, T, it would be how many years. So I know you have that there listed, but if you, I don't know, I just wanted to emphasize it a bit more. So let's do an example, example 1. Calculate the ending balance for 4,000 at 6% compounded monthly for 3 years. So it's that same problem we had at the beginning, but we're not gonna do 1 month and then another month and another month and then add it after we did it 36 times. That would be so much work. So we can use this formula. So if I started from here, I would have to fill out these pieces of my formula. So P, my starting amount, my starting dollar amount is 40,000. R, my percent is 6%. Remember, I changed it to a decimal, so that means we take the decimal point and move it over to the right twice. So it'll be 0.06. Now we need N, and N is how many times per year? We have that word monthly, so that is our N, is 12. And we're doing it for 3 years. T is years, 3 years. Okay, so this is our formula, and we're just going to plug in each one of those numbers into the formula. So do you see how they match up, how they plug them in? P is 4,000, my 1 doesn't change, plus we have R is 0.6, my N is 12. We have monthly, so we have 12 for monthly, and we have 3 years, so we have times 3. Simplify as much as you can, and then from here to here, it's just calculator work. Please practice using your calculator. Each calculator is different, so make sure you can get from that step to your very last answer. Let's do example 2. Calculate the end balance for 5,700 at 4.5% compounded daily for 6 years. So whenever you have something that requires a formula, write down your formula. So your very first step is write down your formula. And then you can start filling in what you need. I need a P, I need a R, I need an N, and I need a T. Let's go ahead and find all these pieces. That P is your initial amount, your principal, so 5,700. R is always your percent. So I'm looking for a percent sign. I see it right here, 4.5%. Remember, we need to change it to a decimal, so I need to move my decimal over twice. This is 0.045. And next, I need N for how many times this is happening in a year. So because this is daily, N is 365. And then we're doing this for 6 years, so my t is 6. Okay, so now I can go ahead and plug in these values to my formula. So I have 5,700 plus 1 plus 0.405 over 365 with the exponent of 365 times 6. Okay, so then we just simplify as much as we can. Maybe I would turn this fraction into a decimal before moving forward. And then punch it all into your calculator. Be very careful in your own time. Make sure you give this a try. Make sure you get that answer that your notes have. So this is how we find an amount raised in interest and it's compounded however many times for over how many years. We have a different type of compounded interest. This is continuous compounded interest, and that's the only word that's being added. So anytime that interest is calculated for a higher frequency of time, times interest is compounded will be of times interest is compounded will always result in more interest. Even if the difference is minimal, that being said, there's a limit to how much interest can be earned regardless of the interest compounded frequency. This leads to a second formula for calculating account balances, which gives you a maximum amount of balance regardless of the frequency or compounding interest. So what it's saying is, even though we can compound it more times within a year, there's a limit to how much I can stretch that value, right? And that limit, the highest one we could get, is that compounded continuously. So here's our formula. The formula for calculating the amount balance of P dollars at an annual interest rate of R for 2 years, compounded continuously, is A equals PE to the RT. So these words mean the same thing. So E is about 2.7. Remember, that's a button in your calculator. So don't let that throw you away. It's not a variable, it's a number. Think of pi, right? P has the same value as before. That's your initial amount, your starting point in dollars. We have R, which is your rate. So again, that's your percent. Remember, change it to decimal form. And T is time, so how many years? So just like before, everything has that same attachment except for E. E is a button. Example 3, calculate the balance for 4%, $4,000 at 6% compounded continuously for 3 years. Okay, so I need to find P, R, and T. E is just a number. So my P is my initial amount, which is 4,000. My R is my rate, which is your percent, 6%. Remember, change your percent to decimal. So we move the decimal to the left, which is 0.06. And then we need a T, time. How many years? 3 years. All right, let's go ahead and plug this in. Let's go ahead and simplify your exponent. And so we're left with 4,000 E with an exponent of 0.18. And you just punch that into your calculator. If I might recommend, first find the E value. It's going to be a very ugly decimal, and then push times 4,000. That should give you a cleaner answer. And we see that compounded continuously gives you a bit more. So here we have 4,788. And the first example we did gave you 4,786. So it doesn't give you that much more, but it gives you a bit more when it's compounded continuously. All right, so that's it for section 4.3. Let me get out of here. So are there any questions before we finish our first lecture? There's a chat on the side. Has anyone been typing in the chat?
I have a question.
Yeah.
The second one, that formula, what's the difference between the first one and the second one?
The first one, second one. Okay. The first one gives you how many times you compound it. So remember that first example before we had any formulas, we worked with an amount and we're finding the percent in 1 month. And then we find the percent the second month, third month, fourth month. You have to find each one separately, right? But that's a lot of work, especially if we're asking for 3 years, 36 months, we have to do it 36 times. So that saves you the trouble of compounding it or applying the percent each time. So there's a way you compound it. So you can have something like monthly, 12 times a year, quarterly, 4 times a year, semi-annually, daily, every day you compound it. Now, what's different between that one and the second one, the continuous, is that word continuously for sure, but also what it does is it's to be compounded every day, nonstop. But because each time it would be such a little change, there's a maximum limit you can get, and that's a continuous compounded amount. So that's the difference between those two. One of them is telling you how many times you're compounding it, so how many times you're calculating it in a year. The second one is just nonstop. It's not much more, but it's a bit more. Now, the verbiage that you want to look for that second one, the one that has an E, P, base E raised to the RT, you will have the word continuously. And that's how you know that you work with that formula.
Got it. Thank you.
You're welcome. Thank you so much for your question, Julio. Any other questions? Was it Julio that asked, or is it just Julio that popped up?
No, it was Emmanuel. Sorry.
Oh, sorry. Thank you for asking, Emmanuel. Oh, I see. So let me read through the chats. Someone said, can I record this? I'm sure you can record it, but I'm also recording it. Someone said she's recording. Someone said thanks. Is the homework due today because it's Monday or next Monday? Well, you don't have any homework due today. If you have any late homework, I guess, yeah, I'll take it. I'll write down a different assignment, one where it's for late homework, and that's something that's before 4.3. We're starting with 4.3. You were supposed to turn everything before spring break, but if you have something, I'll take it for a slight point deduction. This homework will be due on Monday, but because I know you like to ask questions and I welcome these questions during lecture, I actually made the due date on Tuesday. So that way you can come to class with your questions and I'll try to answer them as best I can via Zoom. And then you can have a time to process it, finish it, and turn it on Tuesday. So technically it's due Monday, but the cutoff date is Tuesday. So let me show you again. So on Canvas, let me share my screen again. On Canvas, I have uploaded a module for you guys so that you can go ahead and it has these notes for you. It also has your assignments. So it's under a module. Each week will be a module. And so I have the notes for you. I uploaded both files as a doc file as a PDF, just in case you have a viewing preference. I know some of you might not use Word. I know some of you might not like PDFs. So there's both of them. There's a link for my Zoom lecture, and I'll upload a recording of it. I need to wait for it to transcribe, and that way I can upload it onto YouTube, and I'll put a link there. And I changed the schedule. Let's see if I can check it out. So I changed the schedule. There's less content. I kind of chopped off some sections. Also notice that I cut off a test. We were supposed to have 2 more tests. I'm making it so we only have 1 more just because we lost a week, and I know it's really weird working with online when we were originally meant to be face-to-face. So we're gonna have a quiz every week, and there'll be online quizzes. You'll have an unlimited amount of time, and all your quizzes will be due at the end of the semester. So just in case you have a week that's busier than another, I understand. Your homework will be due every week, and that'll be due as an assignment. There's ways you can turn in your homework. It tells you instructions A, B, and C. Follow one of them. 3, we're going to have just one more exam. It'll probably be online. Your final is on week 19, your finals week, and it'll probably be online. And you still have your SI with you to help you out. So reach out to your SI. Is he here today? Andrew, are you here?
Yeah, I'm here.
He's right here.
All right.
There you go.
Yeah.
Do you have a message for them?
Yeah. Unfortunately, today they don't want us doing the SI sessions. I don't know why. I think that something with the bandwidth, and they just wanted to make sure that all the classes ran smoothly.
Right.
But,
I've heard Zoom has crashed for some people.
Yeah. So they wanted to keep us from using Zoom, but on Wednesday we'll be good to go, and it'll run the same way as this class through Zoom. And I'll set up the link and just be ready to go before class on Wednesday, 4 to 5. And
Sounds great.
we do ask that you have the camera set up for when you come to SI. So during classes you wouldn't have it on, but during SI have the camera on.
So you're gonna see like all the girls with like the hair like this and then
Yeah, you might got to get ready. I don't know.
Alrighty. Okay. Anything else, Andrew?
Just if you guys have any questions, reach out through Canvas or anything. I mean, there's a message box in there, the inbox. Shoot me the questions. I'm willing to help. You know, I know this is hard. I'm a student too. It's hard. It's a lot different than the regular lectures, you know. But
Sure, yeah.
Yeah, we'll be good.
Okay, well, thank you so much for being so patient. Thank you so much for working with us. If you have any questions and you're a bit shy to ask, feel free to email me them, or you can even post them where I have an announcement. If it corresponds to that, I made every announcement so you can comment. I'll open up a discussion board for general questions. I will not include a discussion to this course just because it wasn't in our syllabus, and I know you have a lot going on than to worry about a discussion showing up every week. I do notice 2 more questions. Is the next SI meeting on Wednesday before class? I think it's a question for you, Andrew.
Yeah, it's Wednesday at 4, and
At 4?
I'll put it in the announcements. Are you guys getting those when I put the announcement on the Canvas?
Mm-hmm.
Yeah.
Okay, cool. Yeah, I'll set it up today.
Okay, sounds great. All right, so our lectures, they're just gonna run as much as we need to cover the material. I know you have a lot going on. I know, at least for me, it's really hard to get work done at home. So I'm being very lenient. If you have any questions, talk to me. I think I saw one more question in the chat. Megan asked, are we still doing online homework through the Math25? Yes. So you're still doing your online homework, you're still doing your paper homework. You'll go ahead and turn in your paper homework. You can either scan it if you have a scanner and turn it as a PDF, or you can take a picture of it and send it as an image. It should be a .jpeg. Or if you want to, you can download a free scan app on your phone. That when you take a picture, it can email me a PDF file. But you don't have to do that. You can just take a picture and that's fine. Whatever is easiest for you. You know what's easiest for you, and if you need help, you can reach out to me or Andrew will be happy to assist you. And yeah, you still have your online homework through your book that you need to be working on, and you still have your paper homework. Which paper homework is due? So just as before, what we cover 1 week, the homework will be due the next week. So we have 4.3 and 4.4 this week. So on Tuesday next week is your deadline. Turn in those homeworks, those paper homeworks, and take a picture of them or scan them and upload them into the assignment. You can find the assignment turn-in page on your module, or you can go on the side. There's a tab that reads assignments. It'll say 4.3 homework and 4.4 homework, and that's where you can upload the file. The online homework is due our next test day. So you have pretty much the rest of the semester for the online homework. That was one of the questions. You're welcome. All right, well, have a nice day, everyone. Stay safe, stay indoors, wash your hands. Practice good distance habits, I guess. All right.
Professor, I have a question.
Yes.
The quiz is due next week, right?
Yes, I'm giving you a whole week. So I'll make it due maybe on Monday, just in case you have a busy weekend catching up on homework. I'll make them due on Monday, and I'll open them up right after this class.
Okay, and is it posted already, or are you gonna post it right away?
No, I'll post it. When I post it, I'll send an announcement saying, hey, your quizzes are available. But again,
Okay.
those are gonna, actually I lied. I'm gonna make all your quizzes open for the remainder of the semester, not every week.
Okay.
I'll
Sounds
post
good.
them every week, but you'll have until the end of the semester tournament.
Right on.
Okay.
Thank you.
You're welcome. All right. Any more questions? All right. Well, thank you so much for continuing to work with on your studies. I'll see you on Wednesday. Bye.
Bye.
Bye.